All right, welcome to Lecture 12, Scalability. This is the last of the E75 lectures for this semester. So for those playing along at home, realize that we have nothing going on next week other than your own working on projects. And then in 2 weeks' time, we won't be here, and we won't be here at the same time. We'll be in Maxwell Dworkin, which is at 33 Oxford Street. It's the computer science building. We will be in room 119, which despite the number means one floor up. We've reserved a big room. We'll have some food and drink and a whole bunch of you. And this is for the CS75/CS7 fair. This is the digital photography class. And what you should expect is really just some casual mingling. So we've done this a couple of times now. We'll ask that all of you bring your laptops and have your projects either running natively on the laptop, or it can be on our server or any server that's appropriate for your final projects. And the goal really is just to chat up classmates. We often have a lot of distance ed students who might not even live in the city, this city. We've had folks fly in just to meet their classmates finally, so it's a nice opportunity for them, for you. And we the staff will walk around just asking you, what'd you do? Show us, show off. So it's actually a nice conclusion to the course we found. So that'll be 6:30 to 8:30, so that we're eating into some of the early time slot and later time slot. And again, you'll meet some digital photogs from upstairs who will similarly be exhibiting their work, which will be digital photography. So it's actually quite fun. So we hope you can make it. And in the past, folks have brought spouses and kids and friends. Please feel free. Any questions? No? All right. So today's about scalability. And this is, frankly, I think kind of a fun topic because it's one of those things that kind of bites you if you don't think ahead, at least when you're actually developing not websites for like the local pizzeria, but things for work or things for the real world that may very well have lots of users or may very well in the real world obtain lots of users if you're working on something more entrepreneurial. So today is focused generally on this topic of scalability, but along several different axes. What does it mean to scale your hardware? What does it mean to scale your application, your database? We'll talk about terms like caching and whatnot. So it'll be sort of a shotgun approach to dealing with this issue and that issue and this issue, and that's frankly what tends to arise. If you underestimate the load on your server, or if you poorly design your software, or if you just don't anticipate a whole bunch of users using your site, it becomes one of those frustrating situations where you have a lot of leaks, and every time you think you've plugged one, something else crops up. And so that's why we'll look at a breadth of topics today. In terms of recommended reading, I've never read these, frankly, cover to cover, but these are decent books, at least in terms of skimming or glance at them at the shelf sometime when you're in a store. If you're looking to dive in deeper, I would say that most of these are not terribly technical, the exception being maybe the MySQL clustering book, but they're a decent overview. So you might want to glance at them or read up on them on Amazon, so just so that you have a resource beyond today's conversation. So vertical scaling is going to be the first buzzword for today. So what does this mean? So right now, you've been developing most of your projects on your own laptop, which probably isn't the most performant device, but you've also been using CS75, which supports actually 140 or so students who seem to always be using the server at the very last minute, but it's got decent specs. I think we presented the specs. We're renting a VPS from Servant, which is some third-party company, and they give us a decent amount of RAM and disk space. The downside is that we don't get all that modern an operating system. We've unfortunately not been able to upgrade certain packages because the thing is actually running like CentOS 4, and this is because we were grandfathered in a couple years ago, and it's one of those things where if we try adding a package, other things break. So next semester we're actually going to throw all that out and run the server ourselves, but realize if you've been asking for things for final projects and have been wondering why it's not on the server, it's just because of it's a boat we've been trying not to rock, certainly when you can use your own machines for projects. So there will come a point where the thing breaks. And in fact, I use the same server for a couple of other courses of mine, and there's definitely times of the week where this thing starts to drag and starts to feel rather slow. And we ourselves, the staff of another course, brought this VPS to its knees a year or so ago when we decided it would be a great idea to use Ajax, to have a dynamic interface that students would use in the computer lab on campus to virtually raise their hand when they have a question. They'd click a button, and that web page would say, you're number 3 in line. But the means by which it would update its interface is to poll via Ajax, the server, and say, what place in line am I? What place in line am I? Well, we made the mistake of asking that question far too frequently, and this, too, is one of these funny, frustrating, kick yourself afterward situations, because if you essentially ship code, AJAX code, JavaScript code, that is now cached on users' browsers, and those users, as is the scenario here, leave their browsers open for several hours, you've essentially DOSing yourself by having released bad code, buggy code, poorly designed code. So even on a VPS like this, and frankly, we had like maybe 50 students in the computer lab that night, it's very easy to make stupid decisions that actually start to cripple one's machine. So I brought up a little command, I think a week or so ago, that revealed what was going on inside of a Linux machine. What's this common command on a Linux or Unix system to see what's going on? So top. So top is a command. It's wonderfully useful. It reports somewhat arcanely all of the processes or programs that are running, and it particularly highlights how much RAM each thing is using and how much CPU each thing is using. So if you're ever sitting down at a server, or maybe, frankly, even your own machine, if it's a Mac machine or a Linux box, running top or Mac OS's equivalent activity monitor, if you ever see things like 99% CPU utilization for something like Firefox, probably not so appropriate for a browser to need all of your CPU cycles. So I worry, I'm digressing here, off onto a tangent about Firefox, so let's rein this in and just say that there comes a point where you start to exhaust the capabilities of your server or your own machine. So what can you do? Well, by far the simplest approach to solving a problem of resources is just throw more resources at it, right? If your machine's starting to feel slow, if you're having trouble running lots of application, if your server seems to be having trouble keeping up with the load, well, go spend $50 and double the amount of RAM in the server. It's not all that hard, requires a bit of downtime, but it's relatively easy. You throw money literally at the problem. If you have just one CPU with a few cores on it, but you have a second socket on the motherboard, well, go out and buy an identical CPU, plop it in, and now you've doubled your computational capability. So it costs money, but what does it not cost, or what does it not require of you if you just throw money or hardware at these problems? What's that? So you don't actually have to think very hard or actually solve the problem. Specifically, it requires very little effort on my human part. I don't have to go back and fix my code. So there are many different axes along which you can scale vertically, as is the buzz phrase, which means to take your design, your infrastructure, and just kind of make it better and better and better and better, but you're not fundamentally redesigning your application. If it was deployed on a server with a CPU and some RAM and some disk space, well, the vertically scaled version of that app is running again on a server with with RAM and disk space and CPU cycles, but just more of everything. But there comes a problem. So what's one of the downsides or challenges of just throwing money or hardware at problems like this, do you think? So bottlenecks, how so? Okay, so hopefully that's hopefully this is not the end all. Because hopefully there's a more interesting solution here. And certainly, yeah, you run into bottlenecks. And you run into some real-world limitations. Like, what's the fastest Intel CPU you can buy these days? Yeah, so like 3 to 4 gigahertz these days, and that's it. You can get maybe 2 of them, or maybe in a really expensive server you could get more than 2 CPUs, each of which has multiple cores, but there comes a very real-world limit on just how many cycles you can throw at the problem. RAM, too. I mean, most motherboards are limited to maybe 32 gigs of RAM, 64, 128, even 256 or more these days, but there comes a point where if you need more RAM for that database, you can't get it. So you'll hit that threshold as well. And what's another problem about kind of riding the hardware curve is... Okay, so you have that matter too. So if you're running an older architecture that's 32-bit, you can probably eke out more performance by switching to 64-bit, but things tend to break, at least if you've compiled code that's a reasonable approach, but a lot more effort than just opening the box up, putting in hardware, and then going home for the day. But what's another problem with just throwing hardware at these problems? Maintenance, okay, so you have twice as many hard drives. So combinatorially, you probably increase the probability of failure at that point if you're throwing more equipment at it, sure. But also, even just in the consumer market, right? You can either pay $1,000 for the 2 gigahertz desktop computer, or you can spend $3,000 for the 2.2 gigahertz computer. And that's a bit of an exaggeration, but if you look at most any manufacturer's website, if you're actually paying for the fastest and the latest and greatest, you're absolutely paying paying a premium. And you can look at this on Dell's site, IBM's site. Buying the top of the line is not the best use of resources. So vertically scaling your application has a fundamental limit eventually. You'll hit some real world barriers. And two, you're just probably wasting money. Wouldn't it be nice if instead of spending $4,000 for a super fast computer, I could spend $2,000 but get twice as many slower computers, right? And this is sort of fundamentally what Google was known for originally. I mean, they really went for sort of what hardware was available. They didn't buy the top of the line, which is a mistake that a lot of startups make, but rather they made use of what they could. Lots of cheap hard drives, lots of cheap motherboards, definitely not top of the line, but a lot of them. And that leads us to this alternative to vertical scaling of horizontal. So whereas vertical scaling generally describes just upping and upping and upping your resources by turning a knob, more RAM, more CPU, and so forth, horizontally scaling means don't ride the curve this way, rather get the cheaper, get the slower stuff, but get more and more of it. So more concretely, instead of getting a 3 gigahertz CPU server to serve as your web server, maybe you get 2 1 gigahertz servers because you can spend a lot less, or even more than that. So horizontally scaling often refers physically to actually having multiple servers that are identical, at least in spirit, but that are not as powerful as a typical computer. So what are the implications now for this? Instead of having 1 web server, we now have 2 web servers, and maybe the combination of the 2 equals one of the very expensive one. What does this mean for the design of my application? Like, what kinds of things might break?
Well, so you have redundancy that way.
Oh, so that's actually good. So we actually gain not even just scalability, having more, the ability to handle more load. We actually get redundancy, whereby if one of the servers breaks by chance, we at least can keep the other one alive. And maybe its resources would be taxed, and maybe the site would feel a little slow until we bring the other one online. But in theory, at least, we're still up and kicking. So that's a good thing. Yeah?
Parallel computing, whether your code supports using multiple machines at the same time.
Okay, good. So if your application wasn't designed with any kind of distribution in mind, you might not be able to take advantage of the second computer, right? Your code that you've written in the past, probably, if it's some script, for instance. Let's make this more concrete. So for Project 3, you had to import a pretty big CSV file and import it into a MySQL database. Now, it wasn't all that computationally expensive, but you probably didn't write a very fancy, maybe Hadoop-based script to actually process that CSV and load it into your MySQL database. You wrote a script that top to bottom was supposed to iterate over that CSV file and insert it into the MySQL database. Now, if that script is not 40,000 lines, but if that CSV file is not 40,000 lines, but 40 billion lines, and now you've got to process all of those. Well, just having 2 servers and running the same code doesn't necessarily mean that you've now decreased your running time in half. You now have to actually change your application. You have to change your code and maybe partition that CSV file. This server does half, this server does half, but that's more labor now for me. So it's not as blind a process as just throwing hardware at the problem. What else might break? Consider your own experiences in this class. If there weren't one CS75.NET, but 2 of them, what might break if you run your code, if you upload the same code to both of them? Yeah. Oh. What's that? Okay, so maintenance of code, that's quite fair. It's a downside that now I have my code here and it's here. If I want to make a change now, I can do it. I can make a change somewhere and then distribute the copies to both servers, but this is not as straightforward as it once was. Yeah, so good one. So this is where it's, again, useful to think not about what PHP offers you at this high level, $_session, but how is that actually implemented? Well, anything in that super global is actually stored, as you're implying, somewhere, on disk by default. In what folder? Little trivia. What's that? So the sessions aren't in user bin, they're in /temp typically by default. So that's fine, fundamentally uninteresting until now, because if you have now 2 web servers and you are running the same code on them, let's assume for the moment that users are sort of randomly sent to one web server or another, but we'll revisit this in a moment, how you actually handle 2 servers up at once. Well, what if the user ends up on this server and you call session start in your code and now they have a session, the $_session exists for them, you store their user ID or whatever in that session object, but where is that data really stored? Yeah, on the hard drive in /temp over here. Now, depending on how you implement load balancing, as it's called, between these two servers, if the user somehow ends up over here, maybe by chance, or maybe this server goes down, you can think of a bunch of scenarios that would cause this behavior. Now the user's over here, and all of a sudden, they're logged out, their shopping cart is gone, something that they had saved in progress is now missing because all of that data was over here. So again, very simple things that you might take for granted, like super globals like session, break potentially, unless you think this through. So we'll push back on how to fix that in a bit. Anything else come to mind? Yeah?
Caching?
Caching, how so?
Not sure.
Okay. So, yeah, I can fill in the blanks. So if your application makes use of some kind of caching, which might be as simple as making sure that anytime your PHP files generate some XHTML, why bother re-executing that PHP code again and again? Why not just save the resulting XHTML in a local file, and the next time check, is that XHTML pre-rendered in a directory? If so, spit it out. Otherwise, generate it. So absolutely, if you have a local cache, you're now potentially not benefiting as much if that cache only exists on one server and not the other. So that could come into play too. And anything else? Yeah?
I was just thinking if this could lead to inconsistency in the data, saving the database, saving the database.
So good. If by having two servers, we now have two web servers and two databases, now things start to get a little messy. And also, if you have a database, you probably don't want two copies of it, right? You presumably want centrality. So this is actually an interesting and common sticking point. It's nice to imagine horizontally scaling out your databases so that you have lots and lots of databases. But if the whole point of a database is to aggregate data so that you can do selects and joins and analyses of the rows in that table, now you've got this really challenging wrinkle. If some of your data is over here, some of it's over here, some of it's over here, now these machines, my God, have to communicate somehow. So we'll take a look at this in a moment too. Let me skip over this so that we can actually answer this question. If you now have multiple servers, let's say for simplicity web servers, how can you direct your users to it? Well, I tossed out one idea, which was just let them go randomly. Well, how can, when a user types www.cs75.net and hits enter, how can you randomly send them to the first web server, or the second web server, or ... any number of servers that represent the CS75.net cluster? Well, we actually have a trick from like week 0 via which you can do this. So we talked way early on about DNS. And what does DNS do for us? Easy softball question. What does it do? So, okay, what does that mean, though? Reroute the user as it comes in. Okay.
So that you can take anybody who goes to www.domain route to a particular proxy.
Okay, but what would do that routing from the generic address to a specific server? Not quite, because once an htaccess file lives on a server, so presumably once that file's been executed, you're already at the server in question. But if you scroll back to week 0, so we had this DNS service, and you've been using this by updating records through directadmin over time. Not many, but once per project at least. Well, with directadmin, can you create a new host name that's associated with a domain name, or you can associate a specific IP address with it? Well, the bind configuration file, recall, looked a little something like this, and directadmin hides some of these details, but we did peek under the hood. This is what you would find in a typical server's DNS configuration, named or bind, Berkeley Internet Name Database. You would have rows like this. So www.foo.com might have an A record, 2.264.131.79.131. But it turns out that bind and other DNS servers actually allow you to have multiple A records for the same host name. So one trivial way of sending the user to maybe this server, or maybe this server, or maybe this server, just because they typed in foo.com or cs75.net, can result from just giving the DNS server multiple options. And by default, this software called bind, which again comes with most Linux or Unix distributions, will just round robin its responses. So if you ask cs75.net's name server for www.cs75.net, if it's configured with this configuration file for its DNS server, the first time you'll get back the first answer, .131. The second time you ask that question, what's the IP address for www.cs75.net, you'll get .132, and then .133, and then .134, and then the next time, the fifth time, you get the first one again. So using DNS, which is this very sort of low level, again, week zero topic, you can implement what's generally called load balancing, which means balancing the load, balancing your users across multiple servers simply by returning different IP addresses when someone asks you what server owns this host name or what IP address belongs to this host name.
Where is that decision being made? I mean, where is the software that's actually making the decision?
Good question. Where is the software being made? It depends. So we, CS75.net, have two name servers, ns1.cs75.net and ns2.cs75.net. So if you assume for a moment that those servers just live somewhere on the internet, your computer, your Mac, your PC, knows how to contact those name servers because of the whole DNS structure, whereby when you your laptop asks for www.cs75.net. If it has no idea who in the world has that map, it will go all the way to those so-called root servers for .net, and that root server will say, oh, here are the name servers, NS1 and NS2, for our domain name. So it's ultimately then cs75.net's domain name servers that would make that decision in this case. Or more generally, the DNS servers would decide what IP address to give me. And then my laptop would just use that address its packets via TCP/IP, and contact the particular server that it was told to. Does that make sense?
Well, it sounds like there's other way out there.
Uh-huh.
It's sounding like it's making a decision for you.
Correct.
Whereas if you're doing it on your server yourself, then you're kind of making the decision somehow.
So correct. So this for...
So, but in
Mhm.
one sense, would there be actually a master server if you would have a lot of small computers to decide? That's really where I'm going. That would decide to do the randoming or whatever way to go into one and then split off.
So yes, so there are multiple ways to implement load balancing. One of them, though, is just to implement it sort of implicitly at the DNS layer by informing the world that there are multiple servers that represent www.cs75.net. So in that sense, the DNS servers, NS1 and NS2, are those servers, the big servers that are making those decisions. So what's good about this? What do you like on first glance about this approach?
Equal distribution.
What's that?
Equal distribution.
Equal distribution, right? 25% of the time, requests should go to 131. The next set, 132, 133, 134. But wait, is that true? Can we push back on that assumption?
It's not true.
Okay, push back on your own comment. Sure. It's not necessarily true. Why?
Because ultimately, I mean, it depends upon how the request is made and when the request is made. Ultimately, it may so happen that 131 might be bearing all the load.
But why might 131 be bearing all the load? How could that situation arise? If you yourself just argued that we get equal distribution of load, in other words, 25% of the time.
If the browser remembers the IP address that the name server gave its ask at.
This is the real pain in the ass, if you will, with regard to DNS, is that the whole world caches these responses, including your own Mac or PC, for some amount of time. In fact, associated with a DNS record, and we don't see it here, is a so-called TTL, time to live, which can be generally a few seconds to a few minutes, or even hours, or even days. But the catch is that not all servers obey or respect those TTLs properly. So what does this mean? This means if I am some random user on the internet and I type in www.foo.com, the DNS server that owns or manages foo.com might tell me that the IP address is 1.2.3.4, and this is a valid response for the next 5 minutes. But Comcast might be my ISP. Comcast decides, we deal with a lot of traffic. We really don't like wasting money on DNS traffic. We are going to take it upon ourselves to cache this response, not for 5 minutes. That's too brief. That's stupid. We're going to cache it for 1 hour. Now, this now affects all of the users, all of the Comcast customers downstream. And network-wise, it's not an unreasonable decision because it definitely eliminates a lot of unnecessary traffic because they just return the cached response again and again. But if foo.com sysadmins decides to change its IP address or make some fundamental change, now I, a Comcast user, might be screwed for some 55 minutes. Until my computer actually notices that change. Or more simply, my own browser, my own Mac might just cache that answer. And that's the real pain. Not only does the operating system typically cache DNS answers, so do browsers even these days. So the takeaway is that it's really not a fun process to change your website's IP address. Now, why might you ever do that? Changing hosting locations. So gotcha. So most of you, all of you have been hosting your own domain names with the course. Presumably, they've not been particularly popular websites just yet. You probably don't get a huge amount of traffic, so that's probably just as well. But there will come a time toward the end of the semester, or just after, when you want to, presumably, move this domain name, if you care to keep it, to an actual server so that it outlives the course and your work or your name actually stays functional. Well, there will be a period of time where some users on the internet, because of this Comcast example, will end up being directed to your website on our server. But some users, maybe someone in some random country that's never asked for your IP address before, they might, on that day of change, get the new server's IP address, whoever you happen to use, and so they'll be routed to the correct website. Now, if your website's just a bunch of pretty pictures and largely static content, really not a big deal. You keep your website up on our server for a few days, you bring it online on your server for a few days, you allow a few days of overlap, and eventually no one will know that your website was ever on our server anymore, and we can just delete it all because you have a copy here. But if your website's dynamic and has a database, now what happens? Now you literally have database on the old site, database on the new site, and now you've got really annoying synchronization problems. So when you're actually managing real-world websites and IP addresses are something that you yourself have to manage, huge pain dealing with these kinds of issues for that simple reason. It's a good thing. Caching in general is a very good thing. Decreases load, optimizes response time. Humans tend to like it, but if something changes, then bad things happen. What else that's bad can happen here? So we've got 4 servers answering queries for this server, or for this host name. What's the worst thing that could happen here? Yeah.
Load imbalance.
Okay, so load imbalance. Okay, so let's actually finish that thread. How might that happen? Load imbalance.
Somehow, even randomly, certain processes do more work than others.
Okay.
So even though you're being random, you're not taking advantage of the fact of what your load is when you assign it.
So that's true. So this DNS approach to load balancing is completely ignorant of what kinds of load the users are actually putting on the server. Maybe it's just someone who's checking their email real fast and that's it. Maybe it's some power user who sticks around on your website for many minutes or many hours even. So then you might get this skew, even though, yes, on inbound traffic, it was dispatched 25% of the time here, but that says nothing about how long the users actually spend there. And what about this Comcast example of caching? Is your load really going to be distributed 25% across the board? Okay, why not?
Because for the same user, the request will be cached, meaning he will always go to one server.
Okay, so for that given user, the response, myself for instance, I'm always now going to end up, at least for 5 minutes or for 1 hour, depending on these caching issues, I'm always going to end up on that particular IP address, and worse yet, that's the really worrisome thing. If it's Comcast itself that maybe on a national level is caching that response, and maybe that's an overstatement, maybe it's just regional, but now my neighbors too are going to be sent to that IP address because Comcast's DNS server that my computer by default is configured to use when I connect to the internet is going to return only that IP address again and again. So you very much get skew, but now let's at least remind ourselves what was good about this approach in the first place. There is something compelling here. It's easy, right? And even we are planning on using this for distribution of the course's videos next semester because, frankly, it's so easy. You don't need dedicated hardware that you don't already have. You don't need a machine that we'll see tonight is called a load balancer. You can simply use this TCP/IP-based approach at the DNS level that's already in place. Now, there's another downside. Let's push a little harder. You've got 4 servers. What could happen to these servers that's probably a bad thing? One goes down. So suppose that 131 goes down. So now you have 3 servers, and that's pretty good, right? You're at 75% capacity, and you bought fancy enough servers that you can handle the load that the world is throwing at you, but what is part of your audience going to think? What's that?
1 in 4 is going to be unlucky.
Yeah, 1 in 4, or worse, maybe because of caching, is going to think that your website is down, or they're going to experience that your website is down. Yeah?
I'm not sure when you say the DNS server,
Mm-hmm.
and if I'm on Comcast and I go out to DNS, do I hit a DNS server at the Comcast entry point, or when I hit the service, and therefore they provide me with an IP address to get to foo.com, and then there's a DNS server on that box?
Good question. So, in short, what happens when you connect to the internet via someone like Comcast DNS-wise? So typically, in the simplest case, you have no home router or wireless or anything like that. You have a cable modem from Comcast or equivalent. You have a desktop or a laptop with an Ethernet cord coming out of it. You plug that into your cable modem. Among the responses you get from that cable modem when you boot up is an IP address, a default gateway, a subnet mask, and 1 or 2 or 3 DNS server addresses. And those 1 or 2 or 3 addresses will belong to Comcast, which means when your computer wants to convert foo.com to an IP address, your computer by default will talk to Comcast, and Comcast will answer that question for you. Now, if you consider the slightly more common scenario these days where I've got like a Linksys router or like an Apple Airport Extreme or whatever, and I interpose that device between my computer and the cable modem, very often will your own router, home router, serve as a caching DNS server. And this is actually a good thing because it typically speeds up response times because you only have to go as far as your living room to get a DNS response, at least for frequently visited sites. But even in that case, will your home router likely ask recursively Comcast's DNS servers for answers it doesn't already have in its cache. So,
Then when it hits foo.com, then the DNS server there, it ends up on these.
no, so at that point the DNS process is done. So DNS comes into play at the very beginning of the story when my computer or my home router does not know the IP address for foo.com. But that's one of the first answers that comes back, and once I know the IP address, that's it. Once I've reached foo.com, it must be the case that I know foo.com's IP address because, paradoxically, I couldn't have reached him without knowing his IP address. Does that make sense? So in short, DNS is one of the first pieces of the puzzle.
No, I see.
Okay, yeah.
And maybe the next piece is just routers are the question. Once you know the IP address, you go to the router, right? You get a trace router.
Mm-hmm.
So maybe that's what you're thinking about. That's how you get it there. The way the trace router works.
True. So once you know the once the DNS service has told you the IP address, then you address your virtual envelope to that IP address and your local router, which is probably your Linksys device, followed by Comcast device, followed by more Comcast devices, followed by the rest of the internet's routers, are the next machines. So this goes in a DNS server. So if we summarize this whole picture, if I have my little laptop here, okay, we'll go with desktop because it didn't draw very well. If I have a little desktop computer at home here, and I have a little cable modem here, and I'm connected here, then, this is my router. This is my computer. Then this goes into my cable modem. And now my cable modem is connected to the internet. But the first person I interact with is generally my ISP. And my ISP actually has a server in here called the DNS server, so that when my computer wants foo.com, the request goes here, 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 makes a pit stop at the DNS server, gets back the IP address that I actually want. Now my computer sends out a new request for the web page or the email or whatever it is I'm trying to send or receive. Then the request goes through the ISP, but then to the rest of the internet. And then the rest of these dots on the board would be router, 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 router. So it's Comcast that has the DNS server, but the storyline for today is that this thing often caches, not so. This thing often caches response, this thing often caches responses, and then the stupid browser in your window also caches responses. So it's a tricky thing to chase down when you're experiencing problems related to DNS caching. So sometimes you just kind of have to wait it out. Other questions? Oh, sorry. What's that? Well, you can definitely flush these caches in your computer pretty easily. Usually quitting the browser flushes its cache. Restarting the computer probably flushes its cache. Even on Windows, you can do, at the command line, ipconfig /flush DNS, and that will flush your your DNS records. You can do it on macOS. I don't know offhand the command, unless anyone does. But this thing you can reboot, your home router, but then once you get here, then you lose control. So you can only do so much. Other questions? Yeah?
Why does CS75.net, they have two name servers?
So the general rule is that a website must have two name servers, and this, for small fish like us, who just need a fairly modest server, it's kind of overkill, because then it seems like for us just to run our website, we need to have a web server and a DNS server and another DNS server. So we actually kind of mislead the world. Our DNS server runs on our web server, and we actually bind all 4 of those addresses to our same server. So we essentially have 4 Ethernet cards, and even that's another white lie, inside of CS75.net so that it has 4 IP addresses. And in this way, can we tell the world that ns1.cs75.net actually has an IP address of, I think, .131. ns2 has the IP address of .132. But so does www have that same IP address. So this is common, too, for small fish where all of your services are on the same box. And for us, we very reasonably hypothesized that, well, if our primary DNS server goes down, well, so by definition is our web server going down. So it doesn't really matter if we have a second server serving DNS queries, because the users will still reach a dead end. But in general, redundancy is a good thing. Okay, so there's a lot of problems, despite the simplicity of this DNS-based load balancing. But it is a viable solution, and it's not uncommon. But there are other approaches. You can do what's called layer 7 load balancing, or layer 5 load balancing. This just means at the application layer, where you actually have a device, maybe, between your web servers and the rest of the internet that makes an intelligent decision upon receiving users' requests to which web server they should go. Or it might make a random decision. It's not uncommon, for instance, to visit a website like www.dominoes.com, and then after a few clicks, where do you sometimes end up, if you're familiar with ordering pizzas from this website? www.1.dominoes.com or www.2.dominoes.com. So a very common, or a somewhat common approach these days to implementing load balancing is for the request to come in, maybe just hit one server whose purpose in life, a la htaccess, is to dispatch requests or to redirect requests to very specific servers, not based on their IP address, but based on their host name. It's a pretty simple mental model. If you want to have 10 web servers, I'm going to call them www1, www1, www2, www3, ... www10, so that when a user's request comes into the one and only www.dominoes.com, the only purpose in life of that machine, and as such it doesn't need to be a super fancy machine, is going to be to randomly or somewhat intelligently issue a HTTP 301 or a 302 response that says go instead to www1.dominoes.com, and you go to www3.dominoes.com. The upside of this approach is that if www1 goes down, well, no problem. This middleman can notice as much or be informed as much by a human, and so henceforth he only returns the host names www2 through 10. And you can immediately take a machine out of rotation, so to speak, fairly easily. But what's a downside of this approach of bouncing users to a very specific machine based on its host name, which is now itself unique? www1, 2, 3, yeah. Yeah, now you're kind of revealing a little too much detail to your users. It's not uncommon for users to want to bookmark your site. Maybe they want to bookmark the menu or some reasonably bookmarkable page on your website. And now you kind of in perpetuity have to maintain that URL. You better make sure there's a www2.dominoes.com for any users that might have bookmarked that page or copied and pasted that URL into an email and sent it to someone. And what if that server just plain old goes down? right? Now you have a dead end just because the user's browser or their bookmarks or the link they've clicked leads them to a specific server. So this generally is not such a good thing. It's just unnecessary technically, and it's also a bit sloppy because you're just creating these problems by sending users to a hard-coded name. But on the flip side, what's often the pushback here? What's nice about it? It's pretty easy, right? And that may very well be a reasonable input to this decision problem. So what else can you do? Well, it turns out there are devices that are not web servers that just redirect users to different host names, but they're really routing devices where a request comes in, they realize, oh, this is meant to be a web server request. I know about 10 web servers in existence. I'm going to just relay this request sort of transparently to one of these back-end web servers. And so now the load balancer becomes still a middleman, but a middleman who doesn't punt. He actually takes in the request, sends it to the web server, and that web server may very well, a la NAT, reply to me, the middleman, and then I will hand the response back to the end user. So we might have a picture like this. So we've got a user up there at top, we've got the internet, the cloud in the middle, some random device we'll call load balancer for now in that little rectangle, and then there's 3 web servers behind the scenes. What's really nice about having a middleman now is that he can make all sorts of decisions. He can either just do things randomly, in which case, you're not much better off than DNS, but you do have the upside of if the web servers on the bottom there go down, you can very easily take them out of rotation because the world only now knows about www, which is this middleman here. You can make decisions even based on the username. So if it's necessary, as we'll discuss in a bit, to partition your database, all of my users whose last names start with A are on this server. All my users whose last names start with B are on this server. That might be a reasonable design decision. If you don't need to correlate data across individual users, you just need to keep the same people in the same place. Well, this device could even look at the packet that's coming in, check the cookie, and figure out what is this username, to what server should I send them. So it's layer 7 load balancing in that it can actually take into account application-specific information. It doesn't have to look only at the TCP IP level, the IP address, the port number. It can actually look at the HTTP traffic and figure out to whom it's appropriate to send this response. So better, but now there's a new downside, which is what? Yeah?
But it's kind of like what with HTTPS. It can't look inside the
Good question or good concern. So what about HTTPS? It is a concern if you're using HTTPS from the user all the way to the web servers, but it turns out that these middlemen called load balancers often are called, stupid buzz phrase, SSL accelerators, which means that they actually receive the HTTPS response, but they have the SSL certificate here, not here, and so they decrypt the response, the request, and then just relay it unencrypted to the web servers. But because this is probably your own private network in your office building or in your co-location warehouse, doesn't matter if it's unencrypted at that point, because it's just your hardware. But what's the bigger problem here? Just look at the picture. What problem have we introduced pictorially? Yeah, so this is kind of a huge step backwards. We now have lots of web servers for spreading the load. We have lots of redundancy, and yet we now made this bottleneck in the middle, which is problematic not so much because it's a bottleneck, because from the size of it, it looks like a pretty big server. But if it goes down, now it doesn't matter if those 3 web servers are all humming away. I can't reach them. So how do we fix this?
You have to have redundant load balancing.
Yeah, so now we've just kind of have to push this principle of redundancy up a little higher into the picture. So we actually now need multiple load balancers. And so what's actually quite common, this time I'll try to draw a laptop, so I think that's how people draw laptops. So we have a laptop connected to the internet here. We have, in this scenario, 1 load balancer, but really we could have 2 load balancers, which I'll depict as these 2 rectangles, and then beneath these, can we have 3 separate web servers down here. Now this is a little weird. This is the www layer, this is the load balancing, LB layer, and this is the internet. So this seems a little problematic because now how do I get traffic from the internet to go here versus here? Well, maybe I can give each of these guys an IP address, and maybe I can use DNS to load balance that, but then we're just reintroducing the same problem. So actually a very common and fairly elegant approach is that you actually have the illusion to the world that these two computers are just one device. They have just one IP address, but an IP address that's only bound to the Ethernet card of one server at a time. So you can configure, often if these are Linux or Unix machines with some savvy, you can configure these two servers to be in primary and secondary mode, or primary and redundant mode. Where this guy on the right, let's say, is alive, he's powered up and running, but he is very much passive. He's not supposed to get any requests. This guy is supposed to get the requests, and so by default, your website's IP address, 1.2.3.4, is bound, as they say, to this server here. What this guy is doing, he's not really talking up-down. He is occasionally sending what's generally called a heartbeat to the guy on the left, where it's essentially a question of the form, are you alive? Are you alive? Are you alive? And this guy is supposed to respond, yes, 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 yes. And this guy, too, can ask the same question. So it can be bilateral, and you can both assess each other's health, so to speak, via this process. The moment this guy does not hear back from this guy, what do you imagine, based on this storyline, he should do? He should grab that IP address. So he will make the assumption, if I don't hear back from this guy, probably means he's down, which means doesn't matter if he had that IP address. Presumably, if he's not responding to me, he's not responding to anyone. I'm just going to presumptuously take over that IP address, and so now I become the primary. This guy becomes broken, and now a human has to go fix this device here while this guy hums away. So it's definitely a bit more complicated and definitely involves more configuration savvy. All of this, though, can be done with free tools, and you can buy very expensive hardware that does precisely this. But this isn't bad. So now we have redundancy at this layer, we have redundancy at this layer, and we have the ability to spread load across multiple servers. So we've really taken an intelligent step in this scalable direction. What might the downside of this be, though? Oh, one second. What might be the downside here? So more steps. So you're introducing some more hops, maybe a bit more latency, and that's fair. But what we're gaining is, okay, so we're spending a few more milliseconds, but hey, we can now increase our SLA's promises to more uptime. Yeah?
Connections previously helped with the first machine that went down. The internet connection lost when the second machine takes over.
Good question. If the guy on the left goes down, what happens to connections he was handling? Odds are they get terminated, or they die out, or something bad happens to that handful of users at that split second in time. So it's not a perfect solution.
Although, wouldn't it be possible, if you really wanted to get expensive, to actually have the primary send the information over to the secondary?
Absolutely.
Keep that, that when you get into like banking, when they have the, I think what it's called, right? I'm not sure with the word. You get very high-end.
Short answer, yes. So short answer, yes, you can, with either free software or expensive hardware, have these guys exchanging information constantly, including session information, for instance, so that if this guy goes down, this guy knows, at least up until the last split second, everything that this guy knows. So you can mitigate that. But what's, again, the downside here? Feels like we've found the silver bullet. We've picked a lot of holes in the previous two approaches of having a DNS approach, having one middleman. Now we've got two middlemen, which very smartly share one IP address. That floats is another piece of jargon. It floats between the two of them. So there is a bottleneck here that all traffic has to flow through these guys. But you know what? I'm going to say that PHP is kind of a slow language, and by far are the web servers being taxed more than these devices that can actually operate at layer 3 or layer 4, which is lower and therefore requires less computational power. So I can mitigate that by spending my hard-earned money a little more here and skimping down here and getting more cheaper devices here. So valid, but something that can be mitigated. We still have the session issue unless there's some intelligent load balancing going on here. We have to make sure that the same user is being routed to the same device, or, we'll come back to that in a moment, somehow these guys share session data. All right, so I'll put it up there because I've had to do this myself. It's a pain in the ass. It's a lot more complicated. Right? If you scroll back to what the DNS approach was, you could do that right now by logging into DirectAdmin and telling the world that your website, mydomainname.com has multiple IP addresses. Done with load balancing, so long as those web servers exist. And even this approach of just having one central load balancer, even if you're not sure what the software is called or how you would do it, but we'll toss up some bullets in a bit, it's at least a pretty simple mental model. But now that you introduce this kind of fanciness where you have an IP address that can be sent from one server to another, it can be taken over by the latter rather, and you have some kind of heartbeat going on. I mean, this is, in the real world, doable. A lot of people do this, but it's just more work, too. So it's, again, one of these trade-offs. And I think I deferred a question or a comment before.
If you're partitioning the database, then if one of the servers at www level goes down, you're in trouble.
True. So even if you're partitioning your data for performance's sake, but one of those servers goes down and you've partitioned, again, your database, you might very well have to return a sorry message to all people whose names end in Z or whatnot. But this happens. I think I, even a year or so ago, had this happen with Facebook, where it was working fine for a friend, wasn't working for me. It was presumably because we were on different servers or different databases. So what are the other? So not bad. So more complexity, but this is a step toward what's fairly common, right? Because there's a lot of websites where downtime, certainly for large numbers of users, really unacceptable, right? Like people like Amazon can put a dollar amount on how many dollars they lose per minute if their website becomes inaccessible. So there's certainly justification in the real world for figuring out complexities like this and actually building in a robust and a scalable architecture, but a number of problems do arise. So there's this problem of sticky sessions. So it's the buzzword that describes the need to make sure that if a user is being sent to this server or this server or this server, that their sessions stick to them or to the server. In other words, I can't keep getting prompted to log in just because I'm pseudo-randomly being sent to this server instead of the first one that I logged into, right? Really unacceptable from a user experience to have to constantly log in just because you're sending them to a different server. So how can you actually maintain sticky sessions irrespective of load balancing? Well, you can share storage. And this is a pretty common approach. If the fundamental problem before was that /temp belong just to one machine, well, maybe we could create like a network file system that all of those servers mount. In other words, you have a network like a file server, as you might have in the office, but that file server is accessible by web server 1, 2, and 3, and all of them have a directory or share one directory on that file server. In this case, in that case, if a user ends up here, and session start is called, and some session data gets stored not in /temp, but in /shared, or whatever you call the directory, then it doesn't matter if the user ends up here next time, because this guy has access to the same directory. So does this guy. So does this guy. So shared storage is one approach. The means by which you can do this in descending order of cost is something called fiber channel, which is a very expensive technology, but very much in vogue in enterprises. There's iSCSI, which is much cheaper, a little bit simpler, and uses standard Ethernet hardware. You run the file server bits over your standard Ethernet ports. And then there's NFS, which has been around for years and really requires a few tap, tap, tap on the keyboard, editing two configuration files, one line in each, and you can make available a directory on one server available to any number of other servers on the same network. And it's pretty trivial to do so. Cookies can also be used to maintain sticky sessions if the load balancer is allowed to do some introspection and actually look at the cookie value and realize, oh, this cookie starts with the number 1, let me send it to this web server. This cookie starts with number 2, let me send it there. So you can just exercise some control over where cookies map to. But of course, if one goes down, you might be screwing over some percentage of your users, but at least not all of them, which might be an acceptable cost. Other questions? Yeah?
None of the applications that works in WebLogic or WebSphere allow you to maintain this sticky sessions. Like a checkbox that you check and you basically got sticky sessions. So out of these three options, which ones do they use?
It's a good question, and it really depends. So the question is, which of these approaches for maintenance of sticky sessions do people use? I mean, in past courses, we've just used NFS, and we just have a shared directory, and we make sure all the web servers can read it. Works pretty well, but then your single point of failure becomes your your NFS server, your file server, right? So this is one of the, if you think about it, if you like this kind of stuff, it's great because there's an endless supply of problems. Every time you solve one thing, again, another leak pops up. In this case, shared storage means just pictorially, I didn't leave quite enough room here, but pictorially it would mean connecting these 3 web servers to one thing down here. And that's now a problem because now it's a single point of failure. If the file server goes down, now I've lost all of my users' sessions, even if those web servers are humming away. So then you think, well, I need redundant file servers. Another pain in the neck to actually synchronize 2 file servers because of the speed involved or the time involved in actually moving bits across the wire, a non-trivial amount perhaps, back and forth. But there are distributed file systems for doing this. There are protocols that allow 2 servers to synchronize. But again, it's just more time, more complexity, and maybe more money if you want to have 2 of those things too. But the picture is actually now starting to look like something much more real world. And this is why we're so thankful for the course that, we can use our little bubble of 1 server, and if it goes down, okay, problematic at due time, but at least we can fix things fairly rapidly and not annoy or lose well, maybe I shouldn't go here. So there's perhaps an acceptable cost to annoying a few users, 140 of them, versus spending thousands of dollars to guarantee 100% uptime. So it's a trade-off, ultimately, technically and financially. So how do you do this? How can you actually implement load balancing? So thankfully, there's a whole bunch of options, and a lot of them are free. So not for this course, well, this course probably in a future semester will use a load balance cluster of at least 2 machines so that we can at least hedge against 1 server going down. We'll at least have 1 up and running so that the humans don't have to scurry as fast to fix the problem. But you can do this with any number of downloadable things. So LVS, Linux Virtual Server, is very popular. We used it last year in conjunction with Amazon EC2, which is a cloud computing service. And we had actually at one point for a course 6 virtual machines, so 6 servers to which students could all SSH and write and run their code. And then we had 1 central load balancer and 1 central VM that sent users via this free software, LVS, to any one of those 6. And it actually worked quite well. Perlball is a Perl script, essentially, written in Perl that balances load as well. Piranha is a tool that ships or shipped with Red Hat for some time, which makes this a little easier. Pound is another, UltraMonkey is another. All of those software-based approaches are free. And actually, I should add to the list one we've started using this semester quite happily, HA Proxy, High Availability Proxy, works wonderfully. And it actually comes with modern Linux distros like Ubuntu. Very, very easy to get up and running. What does it do? It implements precisely the story we've been telling. Requests come into the server running this load balancing software. Via your configuration file, it knows to whom to send the data and using what heuristics. So right now, we use round robin just because it's simple. We don't have a huge user base. But last year with EC2, we actually used we actually took into account the load on the servers, which was advantageous because it didn't probabilistically put undue burden on one server. It was a little smarter than that. So many different heuristics exist. Now, in the real world, where people prefer to have brand names on their website or to be able to sort of trust in industry names, you'll have, really in the load balancing world, Cisco, Citrix, and F5 are probably the biggest. And they're also the most expensive. So if you want to get a load balancer, from these guys you get 2 load balancers typically, right? You get them in a HA, high availability pair. Unfortunately, that often means you pay twice as much for them. Although that's not quite the case. But if you buy a pair of nice Citrix boxes, you'll spend, guess how much, for a load balancer that can handle, let's say, several thousand requests per second. 20,000 requests, 50,000 requests. I forget the specs of this particular device. $10,000. Do I hear higher? $100,000 is the price tag on not even the top-of-the-line load balancers. Now, some of that is branding that you'd be paying for one of these companies because all of them are very well known and generally well reputed. Some of that, I'm sure, is the technology. They've got a lot of smart people who have really been optimizing the performance of these things. But the irony or the tragedy is some of these devices are just running their own variant of Linux. So there's a lot to be said, especially for startups, to be considering some of the free options depending on exactly what your load is. If you're trying to start the next Facebook, odds are you don't need to spend $100,000 your first year in operation. Probably suffices to go with most everything free, as Facebook did. MySQL is what they predominantly have used. It's wonderfully free. But F5 is even more expensive because we looked at them too for a consulting gig once. So lots of money. But the upside is they do work really well. It's never gone down in like a year in using one of these. So anyhow, sometimes you do get what you pay for. Why don't we take a 5-minute break and we'll resume on this. All right. So this is great that everyone's chatting. Apparently that's what happens when you all know each other's names. So PHP is a scripting language. It's an interpreted language, which a lot of people take as meaning it sucks performance-wise. And that's kind of true. If you write a program in something like C or C++, write the same program, quote-unquote, in PHP, run them side by side, odds are the C or the compiled C++ version's going to perform much better, much faster than the PHP version. So is that a deal breaker? Well, probably not. So there's a lot of upsides to using a language that you don't have to compile, that's very rapidly deployable, like PHP, unlike something like, say, Java servlets, which must be compiled and redeployed, certainly C and C++ code, which needs to be compiled, and all of this. So it may very well be the right tool for the job. So how can you mitigate some of these concerns, especially if you're going into the next office meeting, you're trying to convince some people that PHP is not so bad as you claim it is. We don't need to use this other language to solve this problem. So there are some very easy optimizations you can employ. So PHP acceleration is the fancy jargon for just making PHP code faster without your really having to do much in the way of intelligent thought. You don't have to redesign your algorithms. You don't have to rethink your own code. You just have to turn on a few switches on your server. So what does that mean? Well, there's opportunities to optimize code. So just as in the compiled world, there are compilers that optimize your code for you and realize, oh, I can compile this for loop or unroll this loop and actually make it execute in the aggregate faster, at least probabilistically. So can PHP interpreters optimize your code for you. Your scripts are essentially compiled at the very last minute. It's just unfortunately they're compiled at the very last minute and then executed again and again and again every damn time someone visits your .php file. The upside is you can open that PHP file, make a change, save it, and bam, you've redeployed the application because that change takes immediate effect. But it's also very easy to employ what's called opcode caching, operation code caching, which simply means that PHP or your web server can be instructed to realize only compile this code once, keep the response around, keep the bytecode, if you will, around, and the next time a user requests that very same page, check your cache and use that compiled form rather than reinterpreting the whole script yet again. Now, how do we even go about doing this? It's frankly relatively easy. There's a bunch of packages, all of which are free, that you can use. We've used at least one of these in the past. I think we still have one of them running on cs75.net, even though it's probably not strictly necessary for the load we get. But in short, you can install most of these free tools, these free packages, using aptitude or apt-get, or certainly compile them from source, or use yum in a Red Hat world. And in short, once you've installed them, maybe tweak the default configuration file, you just get this optimization for free. And the server becomes smart enough to realize that it should keep your bytecodes, your opcodes around for some amount of time so that it doesn't waste CPU cycles unnecessarily. And you'll definitely see a decrease in execution time, at least for scripts that are more than just a few lines long. So, yeah. There is, but it's not necessary because it should detect that the timestamp on your file is newer than, say, what's in its cache, in which case it should evict from the cache the previous compilation. Yeah?
Is there any downside for not always doing it? I mean, like, is there any reason why it's not always done?
Is there any reason why it's not always done? Lack of awareness, to be honest. Sometimes these things are buggy. I've had to clear out the cache manually at one time because for some reason whatever cache we were using didn't realize that I changed my code. So you open up yourself to that potentially, but in theory that should be avoidable too.
And that's just like a bug.
Yeah, no, right, exactly. That's why it shouldn't be a deal breaker. Yeah. No, but for the most part there's few, if any, downsides, but it's not necessarily helpful or needed for many applications or many servers. But certainly when you start to have to think about scalability, this should be among the low-hanging fruit that you go after. All right, so we left off with load balancing. What about, let's continue this thread of of caching. So one of the downsides, too, of PHP is that even though web servers are really good at spitting out static content, HTML files, CSS files, JavaScript files, definitely spitting out PHP code requires more work because everything between open bracket question mark and question mark close bracket has to be read top to bottom, left to right, and interpreted and executed. Now, the funny thing is, even on our websites, we don't often change the course's homepage, for instance. This welcome message has been there for months now. And yet this homepage is implemented by way of index.php, which means there is some dynamic output in there. Not dynamic in that it's changing constantly, but that we haven't hard-coded into the file. We're dynamically generating this based on a template file for the header, a template file from the footer. And this is really stupid, right? If we're not changing the structure of the website all that often, why am I wasting time calling require once here, calling require once here? Why not just save the resulting XHTML? I mean, I could literally view the page's source, copy this, paste it into an index.html file, and I would actually eke better performance out of the server because Apache and many web servers are much better at spitting out static content than they are anything that's dynamic, anything that needs to be interpreted or executed. It's just the way things are. It's very easy to open a file handle, grab the bits, send them out, done. There's no thought involved. There's no CPU. There's much less CPU computation involved in something like that. But why don't we do that? Well, we don't really have to. The load's really not that high on this server. We don't really need to squeeze every single CPU cycle out of it, and so we don't bother. But some sites are much more popular than our own websites, among them Craigslist. So Craigslist, for instance, gets many more hits, presumably, than our own course's website. And if you've ever looked, I believe this is still the case at their URLs, you'll actually see that they end in .html. Now, Craigslist is not the kind of site where users are editing .html files. You're actually filling out forms and clicking submit. But at least the last time I posted like a for sale thing on Craigslist, I was informed that your submission is successful. It will appear in the index soon, within some number of minutes. So what approach has Craigslist decided to take, at least for things like these ads for jobs here and apartment listings? Well, they presumably have a database. They must have a database. When you submit an ad or whatever, it goes into that database. But for performance reasons, they don't want every time a user like me now comes back to search for some PHP work, they don't want to have to query the database and spit out the output for me, and then for the next guy, and then the next user, and the next user, and the next user, because the data in the database is not changing. Right? Craigslist is really optimized for reads, not so much for writes. People post stuff and add stuff, but they generally do it once, and at least if it's a useful, compelling ad, it's going to be read many more times than it was written. Odds are it's written once and read multiple times. So if we know out of the gate that reading static files is much faster than reading dynamic files, and certainly much faster than asking a database for answers and then generating, as with PHP or some other language, some dynamic content, why not just grab the data from the database once, generate your XHTML, and then save that .html file so that any time some random user on the internet comes looking for this kind of job, you just point them at the static content. And you can absolutely then get away with fewer web servers and thus fewer dollars to serve more users. So, what's the catch? Or rather, why did Craigslist have to tell me, it'll appear in the index soon? What are they presumably doing? Yeah. So once in a while, every minute, every 5 minutes, whenever they feel like it, do they actually update that long list in the Boston, Cambridge, Brookline web design jobs category. They don't do it instantaneously because they figure, maybe there's some other person's going to post an ad in the next couple minutes, or maybe a few dozen people might post an ad in the next few minutes. We're not going to waste CPU cycles on you people. You can wait 5 minutes, and we can get away with far less hardware if we just generate this content once in a while, using like a cron job and then querying their MySQL or whatever it is database just once in a while. So caching doesn't need to be anything fancy. It doesn't need to be opcode caching, PHP acceleration, or anything like this. It might just mean common sense. If the goal is to create more static content and less dynamic content, just keep the content you've already generated around, and by definition it becomes static content. So this alone is very compelling. Is there a downside that you can think of? So you do end up storing a lot of files on the server, which may itself be taxing. Maybe, is it any worse than having the database? Maybe, maybe not, but it's certainly something to consider. Just how many files are you going to have lying around? Some operating systems do limit the number of files you can have in a directory. So for a very popular site, you might have to be mindful of that. Yeah, so if you wanted to add a header to this page, you'd have to touch a lot of files. Why do you say a lot of files? Oh, yes. Okay. So you mean not me, the users, but Craig, the guy. So if Craig wants to update the horrific aesthetics of his website all these years later, that's actually a pain and a very expensive one. Because even the stupid yellow thing there about avoiding scams, when they want to add something like that, if they decide we have to add this to all of our pages that are in there, they have to go regenerate all of those HTML files. So that's going to be a little computationally expensive, take some time to generate all of that. But on the flip side, doing it once for all the pages is certainly better than doing it once every time each page is requested. And at least with something like Craigslist, which is fairly linear or chronological, where I probably only care about current or recently posted things, not things from way back when, he kind of has the advantage of a sliding window where we don't have to bother updating those pages perhaps. But it's a valid concern. If you are not using any kind of dynamism or using the include function or require function or server-side includes or anything dynamic, it's definitely going to be a pain to change the site later. So that's the price he pays. I've actually always been amazed that sites like Craigslist and even Google are as popular as they are, since they really do say something about the lack of need sometimes for aesthetics to be successful, which is great for those of us who stink at aesthetics. So, other questions or comments on this? What if the user updates the post? Which I think you can do if you hang on to the special email that they send you confirming your post. Presumably they have to regenerate this, and presumably they do that on some schedule as well. All right, so caching, where else does it crop up? Well, it turns out you can optimize MySQL pretty easily in its config file, which is generally called my.cnf. You can add something like query cache type equals 1, and this will instruct the database, once it's reloaded with this configuration, to query recent caches, to cache recent queries. So that if I do something like select foo from bar and get back a result set with a bunch of rows, what MySQL can actually do, if I've told it to cache queries, is it will cache that response. So the next time, if it's a split second later, I ask for select foo from bar, it doesn't have to search through its tables looking for all of those rows again. It can just grab them from its local cache. And the database engine is smart enough to realize that if I do an insert or an update, what's got to happen to my cache probably? Should get updated or really flushed. Right? You should just empty what was in there and let it be regenerated again. So this kind of query caching works well for what kinds of scenarios, would you say? If the data is not constantly changing. So probably works really well for someone like Craigslist. If they are using MySQL or anything that supports this general idea, works well when you have few writes and many reads. Facebook, would this work well? Yeah, it's kind of less clear. Probably depends on the user, right? The downside of Facebook is that there are a lot of obsessive people updating their status and their profile kind of constantly. So you might end up spending a lot of bytes caching people's information, and it might not be useful for very long if they're really that obsessive. But at the same time, if you're very popular on Facebook, even if you're changing your profile every couple of minutes, well, maybe you get hundreds of requests in between updates, and so maybe you gain something there. But it really depends. But the upside, as this little one-liner reveals, it's pretty damn easy to turn it on. So a la PHP accelerators, it's something worth considering or knowing that it exists. So this one's really kind of neat. And Facebook is known for using this to assist with their scalability. Memcached, Memory Cache Daemon, is a server that you run on your own your own hardware or cluster of hardware. And it essentially stores arbitrary key value pairs. What's really nice about this is that you can generate some content dynamically with PHP or whatever language. And if you realize, you know what, I'd really like to keep this content around, you don't have to implement your own caching engine. You don't have to store it in an HTML file like Craigslist does. Because, again, think back so what you learned in a hardware class or an intro class, going to disk, despite what I said earlier, is actually kind of slow. It'd be nice if I could actually cache my Craigslist posts not in HTML files, but in RAM. And that's where memcached comes in. Because it's a server, it's actually a program that's running and loads on the startup of your physical server. Well, memcached can actually use RAM, unlike something like Craigslist's .html file. Now, that's a bit of a white lie, because if they're using a RAM disk, they could implement the same idea. But the whole point of this tool is that it allows you to store arbitrary key-value pairs, irrespective of the language and the environment that you're actually using. So this little snippet of code here is taken out of context. It's meant to be a bit of PHP code that allows me to do this. So in the first line, I connect, apparently with memcache connect, to a certain host and a certain port. I then I then check my cache. I call memcache get. I pass in the specific cache that I want to check, and I pass in some ID, like the user ID. If I get back a user, that's great. I'm going to go ahead and proceed to use this user. And this user object might not just be their UID and name. Maybe this is a pretty fancy database, and it's a Facebook user. There's a lot of data associated with the user, and it feels advantageous to store that in a cache instead of having to do a huge, massive join on a whole bunch of tables to get all of that user's profile data. But if I've never asked for this user before or not recently, I can connect to MySQL, select the database. I can select star from users where ID equals that number. Then I can fetch the whole object from memory using MySQL fetch object. And then, just so I don't have to do this again anytime soon, I can set the cache by setting that ID as the key and that user object as the value. So memcached really boils down to something fairly simple. It's a service you run. It makes pretty smart use of RAM, and you can store keys and values in it so you can query for them later. And there's a whole bunch of settings whereby you can expire the cache so that if a user does update his or her profile, you would presumably want to expire the memcached key for that user so that you actually get the new data. So this is complete conjecture on my part, and I'll disclaim, I don't actually use Facebook all that often, but I find it interesting or unfortunate sometimes that I've noticed this behavior. And maybe this is a bug, maybe this is a feature. But if you're on your newsfeed page on the login, if you hit reload a lot, at least recently, I've been seeing like status updates from friends that are like 3 weeks old. I know, which is curious because maybe it's because I've been actually kind of habitually hiding. If you know Facebook, you can hide people if you don't really care what they have to say. So I do this a lot to people. So I might just be running out of friends on Facebook, and maybe that's why I'm getting old data. But because when I, at least with my account, hit reload a lot, I'm actually getting different responses, some of which are very old. It's actually been my hypothesis that I am hitting once in a while a server whose cache is messed up. And I actually have some old data in there. So random aside, but again, as we realized before, bad things can happen when you cache if you actually want to see the updated state of your application. And even you, some of you have probably experienced this with some stupid IE or Firefox bug or scenario where you could have sworn you fixed that bug or changed that line of code, and yet you're seeing the same thing in your browser. Well, often our response as the staff has been to flush your cache, restart your browser, and that too is because those things have caches in them as well. Yeah? Good question. So in this instance here, how would this code know if the user has been updated? There would have to be code elsewhere, whereby... Yes. You might be able to set some trigger whereby it just gets expired after some number of seconds or minutes, but there's presumably also a function that says expire this now, and you, the developer, would call that function anytime the user clicked update on their profile page. You would do it proactively. All right, so the last big player here, we've focused a lot on the web server, is the database. So that's been one of the other big themes in the course. We've used MySQL, but really this is applicable to any kind of SQL server in general, some of these ideas. But with MySQL, you've made certain design decisions, some maybe unknowingly, some maybe intentionally over time. And one of them is the storage engine that you use. So the storage engine for a database is sort of analogous to the file system on a hard drive. It can be HFS plus, it can be GFS, it can be NTFS, it can be FAT32. So a storage engine is the way in which the database tables are actually laid out. So you've probably seen at least keywords like myISAM, which is the default engine with MySQL, very high performing, but it doesn't support transactions, for instance, and row-level locking, which means it's not actually great for tables where you need to guarantee some kind of atomic operations without blocking all access to the rest of the table, as by using locks. So then there's InnoDB for that, which supports transactions. And I think a while ago we had a nice little, no, actually maybe in a second. Yep, in a second we'll have a nice little chart that actually compares the two, but really that's a better exercise at home. There's these things called heap tables, where if you actually want to have a table, especially a temporary table, that lives in RAM and not on disk, you can actually use a heap, aka memory table in MySQL, and then you are pretty much guaranteed, if you have enough RAM, that when you insert rows into that database, they're going to get written to the table, but they're going to stay in RAM and not go to disk. And this is advantageous if you want to implement your own kind of cache. Odds are you might want to use the heap storage engine, because if the server goes down, if it's just a cache, probably not such a big deal. You don't need persistency on disk. Then there's this thing called NDB, which is used for clustered file systems, where clustered databases where you have multiple servers collaborating to store users' data. And just to give you a sense of the trade-offs, you shouldn't just blindly use InnoDB necessarily just because you want transactions. You give up certain things. For instance, MyISAM supports full text searches, searching really large bodies of text for keywords and such. You give that up if you use InnoDB, at least in current versions of MySQL, so realize that there are some trade-offs. And this, for instance, is a chart from the documentation that compares just a few of them. It's a little small on your printout, but the URL's down there. So we proposed earlier the idea of having multiple databases. How can we do this? Well, a very common approach with MySQL, and databases in general, but with MySQL especially, is to have a master-slave approach, where you have one good master database that you write all of your changes to, because someone has to know the aggregate view of your current world, your application state. But then, so that you can actually optimize for reads in a site like Craigslist or Facebook, it might be advantageous to have multiple servers that can be read from, but just one server that can be written to. And so you can relatively easily configure MySQL to have a master server that all data gets written to, but then anytime data gets written to it, as via insert or update, those same queries essentially are copied to the so-called slave servers as well. And now your application can be configured to read from the slaves, but only write to the master. And you can do this by maintaining multiple connections with even PHP MySQL code. Even though you didn't always do this, or often do this, you can actually use MySQL Connect, but you can actually get back a return value and keep track of that connection. So you in your PHP code could open a MySQL connection to a master and to a slave, and then based on whether or not you want to execute select or you want to execute insert or update, you can choose which of those connections to use by parameterizing MySQL query accordingly. So what's the downside of this approach? Kind of spoiled it if you were glancing up. What's the downside of this topology? Yeah, it's kind of a theme here. So single point of failure. Works really well, optimizes for reads. It's pretty simple in reality to actually set up, but if your master server goes down, you might be able to continue reading, and so you can see people's profiles, but you couldn't update them anymore. Now, that's not strictly true. You could certainly built-in mechanisms, or you, the human, could race to the keyboard and promote, so to speak, one of the slaves to become the master, and that might take just a few seconds. And if you scripted it, it might take even less time than that. So that's one upside of having this master-slave approach, is that the slaves are all identical copies, or should be, of the master, and any one of them can take over that role as needed. It's not necessarily automatic, but it could happen. And that might be reasonable in an environment where you can tolerate a few minutes or even an evening of downtime so you deal with it the next day. Well, thankfully, just like the load balancing approach, you can have this bilateral communication. Why have one master if you can buy twice as much hardware and have two and have them talk to one another? So in this case, you don't have the heartbeat approach. You don't have a floating IP address. It's not as fancy as that. You just have two master databases, and each one sends queries it receives to the other, and vice versa for updates and inserts. So what this means is that your application can write to either one or two and trust that the response will actually get propagated to the other. Or you can simply, because of this configuration, by default write to just one of the masters, but then trust that if that one goes down, you already have a server in place that's designed to actually accept writes and be the master. So it can be a little more automatic. And then, just so we can optimize for reads or just have a hot standby, we can actually replicate 1 to 3 and 2 to 4, just as we did in the earlier diagram. Now, how can we get our clients to write to master 1 or master 2? Well, we could use one of these things. So load balancers don't have to be used for HTTP traffic. They can be used for SSH traffic. They can be used for MySQL traffic, or any number of other services as well. So that's one approach. We could take the DNS approach, but that comes with some gotchas as well. But if this is within my own internal LAN, so DNS approaches become very interesting again if you have more control over DNS caching, if you don't have to introduce the Comcast of the world, but this can all be done within your local office or your own VPN, then you only have to worry about, say, browsers caching or operating systems caching, which might be more acceptable than ISPs. So here's a fancier picture still, and I think this is ripped right from one of those books I recommended earlier. So you might very well have, this is not crazy, a crazy topology, you might have a load balancer up there top. It distributes load across a whole bunch of web servers. Those web servers, though, might need to write data to one central place so that there's one repository for all your data, and that's the MySQL master at middle right there. But meanwhile, reads can really come from any number of servers. For a popular website like Facebook, where reads are pretty darn common, we might want to send that traffic to a load balancer that's going to dispatch those queries to any number of slave servers. So this might very well be a reasonable design that solves a whole bunch of different problems, and the takeaway is that it's really just a wiring together of a few of these ideas so far. They don't necessarily need to exist in isolation. So what about partitioning? So this is a very common approach too, and this is actually how Facebook originally began to grow. As best I could tell, or as best I knew at the time, they had harvard.facebook.com, mit.facebook.com, and hostname for any other school.facebook.com. And what they did, as best I could tell, is they had a database for Harvard, they had a database for MIT, they had a database for wherever, and you had very nice partitioning. Now the downside is if the Harvard database goes down, you alienate a whole bunch of users here, but you don't affect the schools down the road or elsewhere in the country. So that might be reasonable. 2, you also can vertically scale a little more effectively, at least to an extent, because if you know that you're only going to have 6,500 undergraduates using this site, maybe modern hardware is sufficient for that user base. If we had 1 million users, probably one server is not going to suffice if the site is very popular. But if we can bound the user base, if we can partition the space into more manageable bytes, then we can actually throw hardware and money at the problem a little more reasonably. So with partitioning, we might have this approach. You've got a load balancer that's designed to handle traffic for last names A through M, another setup that's supposed to handle N through Z, but that's only for the reads. You might very well still need a middleman for the MySQL master. And this is kind of a theme. The fact that most of these pictures just have one MySQL master or maybe a pair is that it is actually sort of a recurring problem in database design, that it's really nice to be able to keep all of your data centrally, and it's a fairly reasonable design decision to maybe spend your hard-earned money on the database, vertically scaling it so that you can really eke as much performance out of it as possible so that you don't have to start introducing this application layer complexity at this point. Partitioning your data, that Facebook approach, if it was true at the time, means now if you want to tweak your database schema, like redesign your tables, you have to do it here and here and here and here, and so you begin to introduce a lot of complexity there too. Yeah? Same thing. Sharding means partitioning. Or sharding means partitioning, or traffic comes in and you shard some of it over here, some of it over here. Same thing. Okay, so just slap one, actually I already said it verbally, but there's this theme, especially these days, of high availability, and this generally refers to this kind of picture where it's okay if one server goes down, the other one can immediately pick it up. So this helps address this concern for reliability and uptime and the like. So in short, again, as promised, sort of the shotgun approach, you can play around here with scalability, you can consider this, but it really boils down to rethinking all of the design decisions you've made throughout the semester on various projects. Once you actually have large numbers of users or lots of data, a lot of these interesting or frustrating problems begin to arise. So hopefully at least now you know what kinds of questions to ask, even if the answer's not necessarily obvious. So I did want to say one thing, and I actually wish I weren't kind of ending on this note with our last class, but I actually wanted to apologize on behalf of the staff because I think we have dropped the ball too many times this semester with regard to feedback on projects and following up with students. And please let me say this is my fault. I think I made a couple of mistakes when it came to the staffing of the course, and we've done our best internally to try to pick up those dropped balls. But let me extend a personal apology to any of you and any of you if you felt that the course has not been as responsive on projects and response time and on the bulletin board as we might have. It's something that, unfortunately, we can't quite fix effectively this semester, but I will do my best to avoid in the future. Okay, now I have to say something more positive, since this is the last thing you'll ever hear on camera. So in 2 weeks' time, we have the CS75 fair. We will have some cake with some good conversations. So if on your way out, let me suggest that you say goodbye to the person next to you and a little promise to see them in 2 weeks. So it's been a pleasure having you. We'll see you in 2 weeks.